Okay, hi everybody. So it's New England Dynamics and Number Theory seminar. It's our last meeting, and we're very happy to have Seungki Kim joining us from Ohio. And the title is Counting Problems on a Random Lattice. Welcome, Seungki.
Yeah. Thank you very much. It's an honor to be able to speak here. Thank you, Dmitry, for the invitation again, and thank you everyone for being here. I see there's there's a lot of audience. So the theme of this talk is the following question, where we let L be a random lattice of determinant 1. I'll explain in the next slide what that means. And B be a measurable set in Rn, preferably centrally symmetric, because lattices have that property too. If V is contained in the set, negative V is also contained in the set. And, and the biggest object of interest is when B is a ball centered at origin. So we can think about the length of vectors in L intersect B. And the question is, how is the lattice vectors inside a set or a ball distributed as n goes to infinity? There are nice limiting distribution, and if there is, what is it? So that's the main general question for this talk. So what is a random lattice anyway? Probably most of the audience know this, but I'll go over it anyway. So in this talk, first of all, a lattice L is a discrete co-compact subgroup of Rn under vector addition. In particular, L has to be full rank. And sometimes whenever I give a talk about lattice, sometimes people ask, what's the associated quadratic form? Well, that's just, well, you embed L in Rn with a usual inner product, and that inner product gives the metric and quadratic form. And then we normalize all lattices so that determinant or covolume of L, the size of fundamental domain, is equal to 1. And a convenient way to express the basis of lattice L is to write it as a matrix where on the first row, I put in the first basis vector. On the second row, I put in second basis vector, and so on. And if you do that, that'll form a matrix that's an element of SLNR, well, up to orientation. And furthermore, if two matrices interpreted as bases of lattices, those two matrices, bases, generate the same lattice, if and only if they differ by left multiplication by SL and Z. This is easy to check because the left action by SL and Z is just change of basis of the lattice. So this space that I'm going to call Xn throughout the talk, which is the quotient of SLNR by the SLNZ change of basis action. We can say this is a model for the space of all lattices in Rn. And well, SLNR, being a Lie group, has a Haar measure, left-to-right invariant. And it turns out it's actually a non-trivial theorem by Siegel that the fundamental domain of Xn has a finite mu measure. So we normalize mu n so that the area of volume of Xn evaluates to 1, so that it becomes a probability space on the space of all lattices. And this is what provides the standard notion of random lattice. So the measure mu n tells me how to sample an element from this space. So that's random lattice. There we go. So why do we care about the distribution of lattice vectors? I guess the most reason has to do with lattice-based cryptography, where they need this sort of statistics to determine the parameters for their crypto system. But I figured I don't really have enough time, so I'll go with the most prominent problem of interest, which is the famous sphere packing problem. So the sphere packing problem asks for the most efficient method of packing Rn with non-intersecting balls of the same radii, same volume. And in the figure below here, there are two different examples of packings in R2. And the labels are kind of self-explanatory. This comes from square lattice, in the sense that the center of balls form square lattice, Z2 in R2. And here, used by hexagonal lattice that is spanned by two vectors. And the hexagonal packing actually turns out to be the most efficient, the densest packing in R2. So as you can see from this example, the easiest packings to imagine, to come up with, and often actually the best packings in the known cases. For example, in dimension 8, the E8 is the best sphere packing. Dimension 24, it's Leech lattice. So this is famous breakthrough by Vyazovska. So there's no reason to believe that this is true in general, but the easiest to handle are in pretty good quality are lattice-based sphere packings, where, as in the figure here, each point of the lattice serve as the center of each sphere, and the radius is 1/2 of the shortest non-zero vector length of the lattice. So if you think about it, this kind of has to be to maximize the size of the sphere without them intersecting one another. And we measure the quality of the packing by the notion of density, which is defined by the volume of the ball we use to do the packing, divided by the covolume of L. And again, that's a very sensible definition, because to each point on the lattice, we assign exactly one ball and one fundamental domain. So if we compare the ratio of the two, so that's sphere, and there are many different ways to study it. Like one can look at a very particular dimension, for example, but then part of the difficulty, not the only difficulty, but part of the difficulty of sphere packing is just because you know very well about what happens in dimension 24, that Leech lattice is the most efficient thing. You cannot make it useful to study other dimensions like 23 or 25. So a different way to think of this problem is to try to get some asymptotic result in dimension. And here's the historical first result of such kind. in the early 20th century. It's called the Minkowski-Lafka. I'm not 100% sure if it's the correct way to say his name, but I'll say Lafka. Yeah, Minkowski-Lafka theorem that says in Rn for any n, there exists a lattice packing of density at least 1 over 2 to the nth. So on a first glance, one might think, this looks like a very weak result. It's like exponentially vanishing in dimension. But if you think about it, it's not as trivial as it looks. Like if you try the most obvious example, the Zn sitting inside Rn, integer coordinate points, then you get something a lot worse than this. You get something like 1 over n to the nth. And also, correct me if I'm wrong, but as far as I know, there's no concrete construction in arbitrary dimension that beats this density. If I'm wrong, let me know. But I think it's true. So a little piece of history, this was stated by Minkowski, but proof was provided by Lafka in 1920s or 30s. But then the theorem is actually the best explained by the theorem of Siegel from 1945, the famous Siegel integral formula. So this says let f be a nice function from Rn to R. And if you want me to be more specific about what it means to be nice, we can say f is Borel measurable, compactly supported and bounded, but those conditions can be relaxed to some extent if needed. So let me just say f is a nice function, and then the average over the space of all n-dimensional lattices xn of this data series or pseudo-Eisenstein series or Siegel transform, depending on what you work on. If you average this function over a set of all lattices, it turns out to be just a Lebesgue measure of the function f. So it's a beautiful theorem, and I know at least 4 different proofs of this. All of them are very interesting, but unfortunately, I don't have time to discuss them here.
Excuse me, thank you. Just can you remind us what is the density of the packing?
So it's a volume of the ball that you can use to do the packing, divided by determinant of L.
Oh, the volume of the ball.
Yeah. So, but then the determinant is L. I mean, determinant is 1 by convention that I just said. So here is just the volume of the ball we can use to pack the space.
What do you mean, volume of the ball to pack the space? You mean it's you want balls that are centered at points of the lattice that do not contain more than 1 point, or?
Yeah. So so for example, in this square packing example, it's just the volume of the single ball. Is it clear?
So wait, can you like heuristically say a small density? What you're saying there that it's hard to have a high density, right? You have to look for the lattice that gives you a density that is high.
Right.
What do you mean by this?
I think it's kind of self-explanatory.
Okay.
Well, I think it's illustrated by this picture. On the left, you have density which is not so high, and then you kind of shift
Exactly. Okay, here you have a good density. Okay,
You
but
have a
so
better
in these
density.
two drawings, you fix the radius of the ball? No.
So I guess one could either fix the radius of the ball or the determinant of the lattice one can use, and I choose to fix the determinant of the lattice
Okay, good.
and make the ball as large as one can, which is precisely this number.
So a hexagonal packing corresponds to some lattice that gets
Yeah.
something to the integral or something like this.
I'm sorry, can you say the last part again?
This optimal packing is the packing that, if you want to relate it to the Siegel integral and the fact that it the average of the Siegel integral is equal to the integral of the function. The theorem is stated.
I don't know if I'll relate this to Siegel formula.
Okay. No, but in the next slide, you seem to relate the first theorem to the second.
Yeah.
You said the second theorem explained the first one, so.
Right, and I haven't done the explanation yet.
Okay.
I will,
Sorry.
and just to clarify a little more. So this gives a lower bound on the possible maximal density that can possibly be attained. This is average argument. It doesn't give us any. It's not a constructive argument. It doesn't give me a particular lattice that we can use. And in low dimensions, of course, it's easy to guess, but still non-trivial to prove. And in higher dimension, it's just impossible. Maybe I shouldn't say that, but it's very hard because we don't have very good intuition, geometric intuition in higher dimension.
Okay, and then we have a question in the chat from Julien Trevisan. Small density means small shortest vector also.
Yes.
Any comment?
Yeah, exactly.
Okay.
Yeah, so basically, we want to find the maximum of lambda 1 of L over L being lattice of determinant 1. That's another way to phrase the sphere packing problem. So let me continue and explain how Siegel integral formula implies this Minkowski-Lafka sphere packing bound. So in order to do that, take f to be the characteristic function of B1, by which I mean ball of volume 1 centered at origin. Well, then this pseudo-Eisenstein series becomes a counting function of the number of non-zero lattice vectors sitting inside this ball of volume 1. So by the Siegel's formula, if you integrate this quantity over L, well, it simply gives you the volume of the ball. So that's kind of elegant. So we know that random lattice vectors on average has one vector, one non-zero vector in a ball of volume 1, and it's not hard to imagine instances where L contains more than one lattice vector. For example, if their shortest vector is very small, there can be arbitrarily many. So there has to be a lattice such that L intersect B1 is empty, except possibly for the zero vector. So that's illustrated in this picture here. So the dots are lattice points. This big half the radius of the ball by half. You can see from the picture that you can do a packing with it because the balls are not going to intersect. Therefore, we found a packing induced by this lattice L. We don't know what it is, but we know it exists. By your ball, B1 dilated by half. So it's going to have volume 1 over to the nth, and that's precisely the density given by Minkowski-Lafkatian.
So excuse me, but this is what I was suggesting earlier, that you will take a lattice that realizes like the average. Then my question was, you said it's not a very obvious fact, the first, this first theorem, and have to look hard for the lattice, but here you're just taking a lattice that realizes the average, but presumably there are lattices that do better, no? Than, or how?
Sorry, I'm not sure if I understand the question.
Yes, okay. No, drop it. I'm fine.
Yeah, I'm sorry.
I understood. But this is the explanation how the Siegel theorem implies the first packing theorem.
Yeah. You take F, basically you take F to be characteristic function of ball of volume 1 and then apply the formula and go through this picture and you're done.
Okay, thanks.
But again, we don't know which lattice it is. And I believe that's where the confusion is coming from. But yeah, I'm sorry, I'm not addressing your concern very well.
But also what Bassam says it that it's not the optimal lattice. Probably you can do even better.
It's not optimal, but we know there is something of this quality. And that's not a trivial fact.
And okay.
Like, I don't know any explicit construction that gives us exactly this or better. So continuing, the natural idea we get here is that if we understand the statistics of random lattice sitting inside a ball better, like if you understood more than average of it, then that might lead to better packing density. And indeed, a lot of research in this spirit was done by Claude Ambrose Rogers and Wolfgang Schmidt, very strong mathematicians in the 1950s. And before discussing their work further, here's the main tool for investigating topics of this kind. So this is called Rogers integral formula that generalizes Siegel's formula mentioned earlier. So here let k be a natural number less than n, and let f be, again, a nice function from k copies of Rn to R. Then the same sort of integral as earlier, average over space of all lattices of this pseudo-Eisenstein series where we sum over k vectors, k tuples of non-zero lattice vectors. So if we integrate this thing, this translates into this following integral over Euclidean space, where we have this term, as in Siegel's formula, just simply the Lebesgue measure of f. So in fact, the contribution to this part comes from the k-tuple vectors here that are independent. So if you put in one more condition over the sum here that these k-tuples of vectors are independent, then this is all the term that you get on the right-hand side. And as for the contributions here, so for each m between 1 and k minus 1, the contribution to this term comes from those k tuples that span a subspace of dimension m. And this matrix D is simply, it expresses all the possible relations between k-tuple vectors that span, well, that has rank m. So that's the structure of this formula. And normally in applications, this is the intended error term. And so curving this part is the main challenge in using Rogers' formula. So using Rogers' formula, we can, so one thing we can obviously do is to compute the higher moments of the number. I should have put absolute value here. Compute the quantity of L intersect ball, and then prove well these following theorems. But before I explain, here's a little disclaimer. So these theorems and everything that appear throughout the rest of the talk, the same statements apply for B not necessarily being a ball. It just have to be a centrally symmetric measurable set of certain measure, but moments.
Couldn't hear you for 30 seconds.
Oh, so I was just saying that so all the theorems that's going to appear from now on, I only stated for the case where the set B is a ball, but it actually applies to any centrally symmetric set. It doesn't even have to be convex of bounded volume, but I'm stating it for balls only anyway. So Rogers used this to prove that in Rn there exists a pecking of density, at least some constant, some explicit constant times square root of n over 2 to the n. So that's an improvement from Minkowski-Lafka by the square root of n factor. And he also proved a theorem of somewhat different flavor, but actually essentially the same. It says, so fix V, some positive real number, and let L be a random lattice in Rn. Modulo signs. So essentially, Poisson distribution of mean V over 2. So there is some nice limit distribution here. And then, so these were done in 1950s, and in 2009, or maybe 2011, there was this result by Anders Sodergren, which is Poisson process version of the statement. So here, fix positive integer k, and again, let L be a random lattice. Then as the dimension goes to infinity, the length of the first k shortest vector of L, they converge in distribution to the first k points of the Poisson process on the real half line of intensity 1/2. So this 1/2 matches the 1/2 factor here. And I guess the difference between Rogers and Sodergren's result is that Sodergren's results it says something about how the k shortest vectors individually interact with one another. So
do you take vectors modulo plus minus 1? So you have pairs of vectors?
yeah, vectors up to sign. So yeah, pairs of vectors.
Okay, and also I'm just curious. So Rogers improved Minkowski-Hlavka theorem, but are there any upper estimates up to what point
So
it cannot be improved? Is it known?
upper bound packing.
About Pekins, yes.
So you're asking about upper bound on packing?
Well, is there a theorem that there doesn't exist a packing of certain density?
Oh yeah, there is, and so that actually one uses a completely different method, and that's why I'm suppressing that here.
Okay.
Yeah.
But it's
Yeah,
like how close is Rogers to optimal? Is it, no?
It's actually very far. So for the upper bound, one has like 2 to the some fraction of n. So you have something exponential here. So it's very far.
I see. Interesting.
Yeah, it is. So anyway, so the letter to, yeah.
Just one question, very naive. So the distribution for fixed n, what do we know about it?
So you can express it as Poisson distribution plus some error term that vanishes in n.
And we have some theorems on the speed of convergence, things like this, or?
Yeah, that's precisely my work.
Let's see then.
So these 2 letter theorems are kind of nice because they provide some sort of image of the random lattice vector sitting inside a ball. So when I was so I'll read this first. So they say the lattice vectors inside a small enough ball relative to dimension is kind of random. It's kind of purely random. In the sense of being Poisson. And that's kind of interesting because lattices are highly structured objects. I mean, it's a group. What more do we need to say about claiming that it's highly structured object? It's a group. But then if you look inside such a small ball, then it doesn't even contain a basis of L, then there is a chance that those vectors just roam about freely. And indeed, that's what's going on. So when I study these works, as a graduate student, I was wondering if the size of the ball can increase with n. And I was expecting to get something like b equals log of n, but I actually got something a little better. So in the previous 2 theorems by Rogers and Sodergren, instead of fixing the size of the ball or number of vectors we look at relative to n, we can take their size to be some constant times n to the 1/2, a little short of that. So in other words, roughly speaking, the lattice vectors sitting inside B is free of structure, of course, other than the sign symmetry within the ball of size a little smaller than the square root of n.
You mean the radius here, right?
No, the volume. Yeah, I do mean the volume.
But in the limit, you have a Poisson law with n that is variable. So you're saying that they start looking like the Poisson, but there is no like limit at n goes to infinity.
Yeah, so actually, I gotta apologize. I misstated this statement a little bit. So to be exact, I shouldn't have said length, but I should have said the proper normalization of length, so that instead of the length, I take the volume of the ball with that radius. Yeah, so you have to translate length into the volume.
Okay, okay, that makes more sense.
Yeah, thank you for pointing that out. Yeah.
And what about in Rogers? What becomes the parameter of the Poisson, which is the V? It's the constant in.
Yeah.
One.
So all the results on this slide here and in the previous slide, including the sphere packing bound, the Poissonness and all that, they're all, you can think of them as being of the same strength in the sense that if you look into details, they crucially rely on the same bound on the error term, the intended error term of Rogers' formula that I pointed out before, and which is about this much size in this particular context. So this square root of n, you might guess this is responsible for this square root of n here, and responsible for this square root of n here. If you suspected that, you're correct. So one would naturally want to improve on those error term. I tried to do it, but it seems very difficult because again, it looks very ugly. So instead, Schmidt introduced a ingenious way of getting around it by combinatorial argument, more specifically, sieve method. And I'd love to explain the details, but again, time is limited. So I'll just say there is such a combinatorial argument instead of method of moments, which allows him to only estimate the error term corresponding to k-1 by k echelon form. So this is much smaller than the full error term from Rogers' formula. It has size about again, you're correct. So indeed, Schmidt proves this theorem. So that this is a further improvement over Rogers' theorem that I introduced just now. So there exists absolute constants, little c, capital C, greater than 0, such that for all v bounded by constant times n in sufficiently large dimensions n, then the probability that lattice contains no non-zero vector inside all of that volume, constant times n, is equal to the density function of the Poisson distribution of mean v over 2 evaluated at 0. So this 0, so this 0 matches that 0. So, and the implied error here is an explicit number. So if you set dimension.
Excuse me. So I think it's also 30 seconds of blackout in terms of the sound. Could you repeat?
Yeah, sure. So I was just explaining this line. So this quantity is actually precisely e to the negative v over 2. So if we take v to be a small enough constant times n, sufficiently small property, namely there is no non-zero vector volume that is linear in n. And by the same reasoning as earlier, when I was trying to explain Minkowski-Lavka theorem, this shows the existence of a lattice packing with density at least the constant I picked here to overwhelm the error. So Schmidt obtained something like 0.28 something times n. So there's our improvement divided by 2 to the nth. So this comes from having the radius of the ball.
Excuse me, what do you mean by a half times the cardinality equal to 0? What is the point of the half?
So this is to account for the sign symmetry.
Right, so but if it's equal to 0, it's equal to 0, right? If the cardinality is equal to 0, then a half times the cardinality.
Yeah. This wasn't really necessary here, I guess.
Okay.
Later it will be. Yeah, it's not strictly needed here. Okay, so we have this improvement of sphere picking down. And since then, well, many attempts have been made. So this was proved in something like 1956, 7, and then until today, there have been many brilliant mathematicians making many attempts to improve this lower asymptotic bound on sphere packing. But the interesting fact is none managed to succeed beyond the improvement in the constant part. So in the linear part of n, this part is still not improved to this date. Some people use like random graph theory. Some people used linear programming sort of argument, but it's still constant in n. Anyway, the current best bound comes from Akshay Venkatesh. He gives this humongous number for the constant. So it's humongous compared to the second best record, which was something like 2.2 by Keith Ball. So this is impressive, but it's still linear in dimension. And to be fair, I have to mention Venkatesh also, he did overcome the linear bound by a small, which is still great. So he showed that come for infinitely many dimensions, but those dimensions are like Euler phi of product of primes from